So when we left off on Wednesday, I made some notes on the slide. I added to a little bit from what I'd said on Wednesday, simply because I was nervous about having written this and that confusing you. So I want to be very, very clear. When I wrote equivalence, I'm referring to I have the same amount of my weak base as I do my weak acid, so my conjugate base of my weak acid in this particular case. If I was going the other way, then I would have the same amount of my conjugate acid for my weak base. Why is that important? Because when you're working with a buffer in lab, when you find this point C, and it's this kind of mid region in your buffer region, we know then that I have the equal amount of base to acid. If that's true, then just knowing what my pH is lets me get to my pKa, and then I can directly solve for my Ka, which, as you know, lets us solve for all sorts of things. So the endpoint is also the equivalence point. And what that says is that I have my mole-to-mole ratio of both my strong acid and my strong base. So I've satisfied those two quantities. I also want to re-emphasize why the pH is higher, because at the end, what do I have? I have water and a weak base in there. So if I have water and a weak base at equivalence point after the titration is gone and I've used all my weak acid, then that means I have a basic solution. So my pH isn't at 7 anymore. It's going to be above that. So this is the same reaction. I'm using NaOH and my acetic acid, and I want to know what volume of the 1 molar acetic acid was needed to titrate my sodium hydroxide. So take a look at the graph. What point on the graph is going to tell you what you need, and how much do you think you're going to need? So pause and come back. Okay, so if we look at this one, I would guess region 2 is probably referring to when I have my pKa, maybe it'd be over here-ish somewhere, where my pKa is equal to the concentration of my weak acid and my conjugate base quantities. But when I look at 3, remember, this is going to be the higher pH because I'm going to have more of I'm going to have all conjugate base and water in the solution. So it's going to be higher. So 3 is going to be the spot. And I look down here, and what do I got? I put in 25 milliliters of my sodium hydroxide. Now I can remind myself what that reaction is. That it was this NaOH plus my CH3 COOH. Whoops, I dropped a C. Going to, let's see, water, and I'm running out of room, my conjugate base. OO minus. These are 1-to-1 ratios, right? So if they're both the same concentration, if I have 0.1 molar of both, I'm going to expect to need to use the exact same, or I'm sorry, let me rephrase, start that over. I'm going to expect to need to use the exact same volume of my strong base, my titrant, with my weak acid. So I'm going to guess that in this case I had to have started with 25 mils of my acetic acid if it took 25 milliliters of my sodium hydroxide. So the answer would be 25. No math, isn't that fun? So let's do some comparison. I have my side-by-side of my strong acid and weak acid titrated with sodium hydroxide. So I want to know what can we say about the original acid concentration? And I'm telling you that we've done the exact same experimental procedure. So from this information, do you think the initial acid concentration was the same? That the strong acid was more concentrated, the weak acid was more concentrated, or we can't tell anything without the Kas? Okay, so the key word here, actually there's a couple key words, is that my experimental procedure is the same. So what that means is that I'm going to have my flask, and I can't draw flasks. So my little flask. Well, that's not a bad flask. And if it's the same, then I'm going to put the same volume of my titrant in there. So my initial concentrations of, let's see, I'm definitely starting with an acid, a pH of 1 and a pH of 3. So say that this was our previous problem of 25 milliliters, not 2, 25 milliliters. That means I would use the same volume of the acid for each. So this would be my acid. And I'm going to titrate. My titrant is going to be my base. I can't draw. Don't hold it against me. In the weak base, let's see, what did I end up using? I used 25 milliliters of the strong base to the strong acid, and I used 25 milliliters of the strong base to the weak acid. And we notice again that the pH is higher at the equivalence point, and that's just because at this point, remember, I have my conjugate base floating around. And at this point, all I have is water and a salt. So it's 7 because I've completely neutralized this. This one has water and my weak base floating around. So if they're the same concentrations, my sodium hydroxides for both, and I've used the same volume, that means my mole-to-mole ratio is going to be the same. My mole-to-mole ratio is going to be the same. That means that my molarity, my concentration, had to be the same. So if I want to titrate a weak base with a strong acid, what do you think the pH is going to be at the equivalence point? Higher, lower, or about the same? In other words, more acidic, more basic, or neutral? Okay, so let's see. Let's just start off with the same weak base that we've been using, CH3COO minus. Put in phase labels this time. Plus a strong acid, so let's just go HCl. Let's see, what are we going to get here? I'm going to protonate my conjugate base, and I'm going to get my weak acid out. COOH plus water. So what that tells me is that I'm going to have a weak acid in the solution after I'm done titrating it, after I have my equivalence of my strong acid and my weak base. So I'm going to have a lower pH. And here we go. Here is my equivalence point right here. So I am going to have a lower, which means that my solution is going to be acidic. So in our next video, what we're going to see is how we can start working with this information to do things with it in a lab.